Hey everybody, and welcome back to the Moonshot channel. Last time we started evaluating our best ideas from brainstorming, but I had a few things that I wanted to look into before I felt ready to make the final decision about any of these different components and move forward to the preliminary design stage. First, I wanted to dive into the European dataset some more. I realized that they had this new ERA5 dataset that you can access via an API. It's higher resolution than the ERA interim dataset and it goes farther back, so it sounded great. So I did some experimenting with the API here in order to access the ERA5 dataset, and I found a couple interesting things. First, it only goes back to 1979. The documentation I was reading before said it went back to 1950, but when you go and click this, you see that they do talk about 1950, and it seems like the intention is still to go back that far, but you know, it's a massive amount of data, 9 petabytes they're saying. So yeah, I'm not going to be able to download that. Even if it were available, I couldn't go and just bulk download that. Not only do I not have the capacity, but the time it would take to download 9 petabytes of data, yeah, we would be sitting here for years. So that's just not practical. But I will say that the data set itself is awesome. 1/4 degree resolution, a really nice like a UI here within the web browser you can use to select different pressure levels, different variables, different times of day, you know, the date, whatever. And then you just hit the submit form button here, and it'll bring you to the next page, which is the queue. And you'll see it immediately, it's ready to go. Now, you'll see in my queue here, I've already got this older request. Now this I did with the Python API. So if I go back, now all this stuff, I can go in and put together a simpler request. So say just this column. And yeah, I might want these times a day. Sure, this is a fine date to choose. I can click this show API request. Now it goes and compiles all that into nice Python code that I just copy and paste into Spider and run. There is a little bit of configuration you need to do. You need to install the API toolkit, and then you need to also install a license file that has your API key in it. So that's they walk through how to do that on the website here, but you know, it's once you have that in hand, this makes it really easy to go and set up a loop or do some sort of multi-threading approach to submit requests and get thrown in the queue and download everything that you need. But the problem is that the queue goes on forever. As you can see here, this request that I submitted, yeah, well, here it is, has been queued up for 1.5 hours. And that's just not going to work. This is 1 day's worth of data. Now, I think that the file size, like I have in the past submitted requests using that API and received 1 day's worth of data, and it was a lot smaller than the 4.2 gigabytes that they claim here. So I think it would end up being something more along the lines of 500 to 700 megabytes per day, especially if you're a little selective with what pressure layers you want. But still, over the course of the full time span, you know, I would fill up the entire 4 terabyte drive and then some that I got for this project. So I need to find a better solution to housing that data, which I think I have. I'll get into that in a few minutes here. But for now, what I want to do is experiment with the data that I already have in hand, the NOAA reanalysis 2 data. So I'm moving forward on that front. I do want to come back to this later though, especially if after building a system using the NOAA reanalysis 2 data, we're still not achieving our goal, our accuracy goals that we've set. So if that's the case, then I'm certainly going to come back to this because this has a significantly higher resolution than the NOAA reanalysis 2 data. That's 1 data point every 2.5 degrees, both along latitude and longitude axes, whereas this is 0.25 degree resolution. And so, you know, you can think about that in terms of just a single example grid. this has 100 data points for every one that the NOAA reanalysis 2 data set has. So that's absolutely massive. And that's why these files are so big. So anyway, okay, so what I'm going to do is just stick with the NOAA reanalysis data for now and build some mock-up solutions with that. In fact, build a whole prototype using that. And then if I need to, come back and revisit this data set and try wedging this into whatever solution I come up with. Now, to that end, even the relatively low resolution of the NOAA data sets still make for some pretty big files. I've got almost the entire 4 terabyte drive that I bought for this project filled up just with NOAA data. So training a neural network on all these would take an absurdly long period of time, especially if we want to experiment around with different architectures and data structures. Further, a couple weeks back, the head of NOAA surprised Congress by announcing that there were some serious concerns that the new 5G technology that's being deployed around the world right now could interfere with certain satellite sensors, and in so doing, throw our ability to forecast storms back by up to 40 years. Now, there's a lot of debate on this issue, especially from the industry that's trying to deploy these networks. But in the case that NOAA is right, I decided to do a little research. Now, these issues brought me to read up on denoising autoencoders. An autoencoder is a sort of unsupervised deep learning algorithm that learns how to reduce the dimensionality of an input image or, say, a 3D spatial data structure like we have here and store it in a one-dimensional array of a given length. Now, the size of that array dictates how much fidelity we keep. There are several types of autoencoders, but the one I'm interested in is the denoising autoencoder. This thing feeds an image that's had some noise added to it through a neural network, which learns the sort of features that are in there and describes those in a short vector. That vector then goes through the decoder portion of this thing that learns how to reconstruct the image. So the output image is then compared against the clean input image before the noise was added. And so by doing this, it learns how to both remove the noise and also store it in this encoded form that takes up a lot less space and is also a nice clean one-dimensional vector that we can use as input into another neural network. Now, this can do a few things for us. First, it can take these hundreds of gigabytes of data that we have and let us use them to train a convolutional neural network once. Yeah, training is going to take some time, but once we have that encoder trained, we'll be able to use that instead of having to retrain the convolutional neural network along with all the other branches of this big thing over and over again each time we want to make some small incremental improvement to our system. Second, we can go big with this. It's going to be pretty front heavy, but what we can do is bring in the full data set. We don't have to just look at this 25 by 25 pixel box around the storm, but we can bring in the full globe and all the variables that are available in the reanalysis 2 set. Now third, this will let us take that encoded data and feed it through several different types of algorithms. We could use a simple fully connected network that pulls together this data along with track data and perhaps some other sources as well. Or we could even swap out that fully connected network for a random forest or a support vector machine. We have a lot of flexibility here now since we're no longer working with spatial data, which is something that we would want to use a convolutional neural network for. And finally, this should also make our system more resilient against potential distortions to our input. This could be caused by that 5G interference that I mentioned before, or some other future unknown issue that we haven't yet learned about. We'll really be future-proofing our system to some degree by using this denoising autoencoder. Anyway, I think you can see where I'm going with this. Autoencoders are a key piece of this puzzle, and one that I never saw anyone else using during my initial research. But this is another example of why the engineering design process is iterative. I discovered a vital clue of solving one of my issues while researching something completely different. And that's oftentimes how big breakthroughs happen. So going back to our mind map, I'm going to throw autoencoders up there, and along with it, a possible design involving autoencoders that will reduce the dimensionality of our data and enable us to take a more modular approach to this problem. I think we finally have a workable path forward. All right, that's it for now. In the next episode, we'll start taking these final building blocks and assembling a preliminary design. Thanks for watching. Moonshot out.